Hello, and welcome to Pro Knowledge Station.
We are going to answer a beautiful question from the history of mathematics. It is called the Basel Problem, and it asks for the exact value of the infinite sum, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, and so on forever. Let's write the problem clearly. We want to find the exact value of the infinite series, the sum from n equals 1 to infinity of 1 over n squared. This is not a geometric series, and it does not telescope, so it is not obvious how to compute it exactly. But Euler found an amazing way using the sine function. Before we jump into Euler's method, let's build some intuition. If we take just a few terms, the sum grows, but very slowly. For example, 1 plus 1/4 is 1.25. Add 1/9, and the sum is about 1.36. Add more terms, and it approaches a value around 1.6. So the series converges, but what is the exact value? That is the mystery. Euler's key idea was to connect this sum to the roots of the sine function. We know sine of x equals 0. At x equals 0, plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Let's visualize the sine curve and mark those zeros. Here is the clever step. For polynomials, if you know the roots, you can factor the polynomial into linear factors. Euler used a similar idea for sine. Since the roots are at plus or minus n pi, the sine function can be written as an infinite product. He wrote sine of x equals x times the product over n of 1 minus x squared over n squared pi squared. Let's write the key formula. It is more convenient to divide both sides by x, so we isolate the infinite product. We get sine of x over x equals the product from n equals 1 to infinity of 1 minus x squared over n squared pi squared. Now we use another representation of sine, the power series. Sine of x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial, and so on. Divide by x, and we get 1 minus x squared over 3 factorial plus x to the 4 over 5 factorial, and so on. Let's write that series. Now comes the heart of Euler's argument. If we expand the product, the coefficient of x squared comes from picking the x squared term from exactly one factor and the constant term from all the others. That coefficient is the negative of the sum of 1 over n squared pi squared. So the product begins as 1 minus x squared times the sum of 1 over n squared pi squared, plus higher powers. Let's write that carefully. But remember, this product equals sine of x over x. That means the series expansions must match term by term. So the coefficient of x squared in the power series must equal the coefficient of x squared in the product. From the power series, the x squared coefficient is negative 1 over 3 factorial. From the product, it is negative the sum of 1 over n squared pi squared. Therefore, those two must be equal. Let's set them equal. Now, we solve for the sum. First, cancel the negative sign on both sides. Then, multiply both sides by pi squared. We get the sum from n equals 1 to infinity of 1 over n squared equals pi squared over 6, because 3 factorial is 6. And that is Euler's famous result. Let's quickly check the numerical value. Pi squared over 6 is about 1.645. That matches the partial sums we estimated earlier. This confirms the result and shows how precise Euler's method is. To summarize, Euler connected the roots of the sine function to an infinite product, then compared that product with the power series expansion. By matching coefficients, he extracted the exact value of the Basel sum. This was a groundbreaking result and a beautiful example of creativity in mathematics.
Don't forget to like this video, share it with your friends, and subscribe to Knowledge Station. Thank you for watching.